Hi there, this is the second video of a two-video series on face alignment. We are introducing a method that solves face alignment by explicit shape regression, which is a method in the category of machine learning. In the previous video, we have talked about the testing stage, and in this video, we're going to focus on the training stage. So in a previous video, we talked about given the prediction model on a certain image, how do we find the landmarks? If you haven't watched the first video, I recommend you watch that first, because in that video you would understand what is in the prediction model and how they are applied. And in today's video, we're going to talk about the training stage. For the training stage, you're given a lot of images that are pre-labeled, labeled with the landmarks. And basically you tell the computer, this image of the person, the shape of the face should be like this. And tell the computer, if you're given an image of a person like this, then the shape should look like this. And the computer learns and stores what it has learned in the prediction model. So next time in the testing stage, when you give the computer a new image, it will be able to estimate what the shape should be like. In the previous video, I already talked about what's in the prediction model, and let's have a look at it. There are mainly three things in the prediction model. The first thing is the average shape, which is shape 0. The second thing is that in the 10 stages, for each stage, we need to extract 400 pixels to know their locations. And the third thing is we need to train the ferns. And for each fern, there will be classification questions, and at the end, at each leaf, there will be a delta landmark. So the first two things are relatively easy to explain. We will explain these two things first. The first thing is the average shape. And the average shape, it's simply averaging all the training shapes that we get. So we add all of them together and divide it by the number of faces, and we get this average shape. For the second thing, it's the extracted features. And we also do it very simply. We take the center of the average shape, and then we just randomly select points that are in a circle relative to the center. So we just randomly generate the feature points. Usually this is good enough, but if you want to do something more, like in the second paper, you can introduce a probabilistic prior that favors the points that are around the eyes and nose and mouth. So because they think these points are more interesting, so they can favor these points. So you can extract more points in this region and extract less points on the cheek. But just randomly selecting the 400 pixels is already actually good enough. Now we come to the third thing, which is the fern. And again, for the fern, we need to get the classification questions. We need to pick 2 pixels from the 400 pixels, and we need to set a threshold. And also we need the delta landmarks at each leaf. Now first I'll talk about an easier to understand method on how to determine these questions and these landmarks. And during this process, you'll be able to understand the mechanism of the fern. You'll be understand the question, how come when we ask these questions, do the classification and add a delta landmark, is going to make the result better. And once we understand the mechanism, we will move on to a not so straightforward method, but more efficient method on determining the parameters of the ferns. So now first the easier method. The easier method, it's simply for the pixels, we just select them randomly. Out of the 400 pixels, we just select 2 of them randomly and set a threshold that within a range, but it's also very randomly. And this way we generate the 4 questions. And with these 4 questions, we'll be able to classify all the training images into 16 beans or 16 groups. Now imagine there are many training images. For example, there may be 2,000 images. So with 2,000 images, at each bean you're going to have around 125 images. And how do we get the delta landmarks? Let's take a look. Now these are the ground truth images, and these are the current shape. So how do we get the current shape? Turns out we would let the image, as we train the prediction model, let's say we have trained up until this point, we have trained all the ferns in the stage 1 regressors. We would make the image go through the testing stage up until where we have trained. For example, for this image, as it goes through the testing stage, after we apply all these regressors, it will look like this. And for another image, the shape would look differently. And as we train the next fern, we will use the current shape like this. Now, pay attention. If we train, let's say we have trained the first fern, then we would apply the first fern to the image again, and the current shape would be altered slightly. And then we train the next fern, we alter the current shape slightly, and then the next fern. So now we understand how we get the current shape. Using the current shape and the ground truth, we will determine a delta value. That is the difference between the current shape and the ground truth. Now this is a 388 dimension vector, given that we have 194 landmarks in our model. And once we add this vector to the current shape, it will become the ground truth. So remember that we have done the classification based on the feature points. For example, if we look at these images, we would see that the edge of the face for the first image is a little bit to the left. We want to move it right a little bit. And also for the second one and for the nth one, the face is a bit to the left. But for the third one, you can see the edge of the face is to the right. So suppose that we had randomly selected these 2 feature points. You will see that the difference between these 2 feature points are big. Like here, this is very dark, but this is bright. So it's big for the first, second, and the nth image. But it's small for the third image because both of them are on the face. So using this feature, we will be able to classify these images into a same group. Now suppose we have maybe 2,000 images. They're not only just these images, but let's say image number 19, image number 24, and so on are also classified into this group, meaning that they need the face to be adjusted to the right a little bit. Then we take all these images that are classified into the same group, and we take an average of the deltas. And then we multiply a damping factor, which is smaller than 1, to make the resulting delta value very small. And the good thing about making this small is to allow us to have multiple stages. And also making this small would prevent oscillation. Imagine that we do not have the damping factor, then the face would, after adding the delta, it might have gone too far to the right. And then next time we will need to adjust it to the left again, and then to the right again. That would be called oscillation. It would make the system not stable. So that's why we want to have a damping factor here. By the way, these are just selected based on 1 feature point, but in reality, because there are 4 questions that we ask, there are 4 pairs of feature points, so there might be not so many images here, but some other images might be classified to other leaves because maybe another question asks about the eye, and let's say these remains in this group because the eye needs to be bigger, but these two are moved to another group because the eyes needs to be smaller. Now, a thing worth mentioning is that the current shape is always a linear combination of the training shapes. And this can be proved because the average shape is the linear combination of the training shapes. And then suppose the current shape is also a linear combination of the training shapes. We will see that the deltas, they are the difference between the average shape and the current shape. So these are also the linear combination of the training shapes. And then this delta landmarks is a linear combination of these. So this is also a linear combination of the training shapes. And as we add these two together, the new current shape will also be a linear combination of the training shapes. So this has proved this statement. And for this statement, the significance is that the current shape is guaranteed to lie in the subspace that is composed of all the training shapes. So for this 388 dimension vector, it's significant that we know it's constrained within the subspace, because this way we would know that the shape would always look like a human face. We would not have, say, the eye moved here and the eyebrow moved here. Now we have explained the method that we just classify them randomly, which is actually good enough. With this method, we will get 4-point-something error. And sometimes these classification questions doesn't make too much sense. Say maybe we have selected a point on the cheek and another point on the cheek, and maybe it doesn't have too much classification power because for almost all the training images, we can expect that these 2 pixels, their intensity would be very much the same. But still, it's okay because even though some of the questions might not have too much differentiation power, others might have. And even if it doesn't, then for the next turn, it might have. So we are always progressing towards the ground truth. Now, 4-point-something error is already good enough, but can we do it better? Yes. In the first paper, they report 3-point-something error, and they have a mechanism that computes the maximum correlation to help find the pixels that has more differentiation power. So now we will go into it and try to understand their method. But it might not be so straightforward, so you might need to repeat this part a little bit to understand it, because I did that. So again, we have the ground truth and the current shape. In order to find the pixels that are strong classifiers, we would go through a process like this. Let me first show you the process and then explain why I did. So first of all, we would randomly generate a 300 by 88 dimension vector. And then we will do dot multiplication with the deltas, delta 1, 2, 3, and n. And we will get a scalar value, d1, d2, d3, all the way to dn. And on the other hand, for all the 400 pixels, we would take all their combinations and we will find the difference. So for example, this is the difference between pixel 1 and pixel 2 for the first image. And this is the difference between pixel 1 and 2 for the second image, the third image, the nth image. And this is the difference between pixel 400 and 400 for the first image, and so on. Then for the next step, we will take these scalars and make it a n-dimension vector. And on the other hand, we have all these n-dimension vectors. We will correlate these vectors and try to find the one with maximum correlation. Let's say it's this one. And after we have found the maximum correlation, we will say, okay, we're going to select these 2 pixels, and the threshold is going to be a random number within a certain range. And this range, this max difference, is the maximum value of all these values, all these differences. So this is a rather complicated process, and now I'm going to try to explain why they use this process to select the feature points. First, let's have a look at correlation. I'm not going to give the formula, I will just have a look at the concept with you. So here you see this is the price of gold, and this is the price of silver. We can see that their change are very much in the same trend. So these 2 values would have a high correlation. On the other hand, if we have another value, let's say the stock market of China, it's like this. And the real estate market value is like this. Then these curves would have not so much correlation with the gold compared to silver. So higher correlation means similar fluctuation. With that in mind, let's have a look at this method. So first, the randomly generated delta R, it can be anything. It specifies a direction of change. Let's say its direction of change is moving the edge of the face to the right a bit. Maybe it doesn't modify the eyes and the nose so much, but it modifies the edge of the face more. And then as we do the dot product, it's like doing a projection. So we have 2 vectors, and we would project one vector to the other. So we already know that delta 1, it's moving the face to the right, just as delta R. So these 2 should have a higher value. For delta 2, it also needs to move the face to the right. So D2 will also have a higher value. And for delta 3, it needs to move the face to the left. So we multiply these 2 vectors, we will get a very big negative value. And then for the nth one, we will get a higher value. And say there is another one in the middle, of which the face is already very well aligned, then this delta times delta R is going to get a very small value, around 0. So this is how the vector on the right changes. And for the vector on the left, if we had picked the 2 pixels just like in the example that we went through, then these 2 pixels will have very strong differentiation power with respect to delta 1. Because for the first image, we will have a very big difference. For the second one, also very big. For the third one, it's small, maybe close to 0. And for the nth one, it's also very big. So you can see the trend of these pixels are roughly the same. So this way, we have selected the pixel that will result in a delta that is very similar to delta R. Now pay attention just to make sure that I do not confuse you. The delta landmarks that we get at the leaves, they're not delta R, but an average of the deltas that falls into the same group. So this is an average, but not delta R. Delta R is only used to help select the feature points with strong differentiation power. Now for the fern, to generate the first question, we would generate a random delta R and find the 2 pixels that are most related to delta R. And then for the second question, we would generate another delta R, which is different from the first one, and we will find 2 other different pixels and the threshold. And then the third question, the fourth question, and so on. We'll be able to classify the images into all these 16 groups. And then for each group, we take the average times the damping factor. We will get the delta landmark of that group. Now, one more thing to mention is that for the training stage, you get to select the number of stages in a firm. So you get to say, for all the firms, I can select 4 questions, or I can select only 2 questions. If there are only 2 questions, then all the 2,000, let's say 2,000 training images will fall into 4 groups instead of 16. And then we will get 4 delta landmarks. But as the researcher has experimented, usually 4 questions would be an optimal number to go with. Now here's to show you what happens in the beginning. Before any ferns are trained, the current shape would be the average shape. And then the first fern is trained, and all these results are altered by the first fern. And then the second fern, they're altered again. And many ferns later, it would look like this. And the next fern is trained based on this shape and this delta. So now we have explained how the variables in the prediction model are trained. Here are just some comments on the method. Remember that the current shape is always a linear combination of the training shapes, and it's a result of the average shape adding all the deltas. So we take all the deltas of a stage and we do principal component analysis on it. Then we get the number of bases, the number of principal components in each stage. For example, in the first stage, there will be maybe 3 of them. The second stage, maybe only 5 of them in all. This accumulates. And as it goes on, until the 10th stage, in all we would have 30-something components. And this is a visualization of the major components of each stage. You can see that in the early stage, the component, let's say the first component, it turns the face to the right, and the negative of it turns the face to the left. And the second would tilt the image to the left or right, and the third will enlarge the face or make it smaller. So the principal components in the first image would make larger changes. But in the final stage, it would make finer changes. For example, it determines whether the mouth opens or not, or whether it smiles or not. So this way, although nothing was done to explicitly guarantee this, but as we train the model, it automatically encodes the regressors in a coerced to fine manner. So these are the coerced, these are the bigger changes, and these are the finer changes in the later stage. Now, given what we had learned just now, it would be easy to understand this figure. This figure shows as the stage progresses, the average distance between the selected features. You can see in the early stage, because it makes larger changes, therefore the distance between the features would be large. But as we move on, the distance between the features would become small to make the finer adjustments. So in this slide, we show the typical numbers of this method. Now, most of these methods can be changed, can be adjusted. We can say we don't want 10 stages, we want 9, we want 8, we want 12. But these are the typical numbers. And a few things to pay attention to. The number of training images would be around 2,000 would be good enough. 1,000 something, also very good. And the training time on a PC would be around an hour. And the test time on a current day PC would be around 1.2 millisecond. Now, because when we apply the model, it only does classification and addition, so this method is very, very fast. And on an Android phone, it would run in the range of 10 to 20 milliseconds. That's why this method can be used on a smartphone and make apps like MSQRD, and the app would have real-time performance. Again, the testing error is 3.3%. Now, this method can also have other applications. For example, it doesn't have to estimate the shape of a human face, but it can be other shapes, for example, a cat's face. Or we can train the model with different orientations of an articulated object and use this method to estimate its pose. It also can be used to segment anatomic structure in medical images. So this is the pseudocode for the training stage. You can pause and have a look. And this concludes our 2-video series on face alignment. I have also included the links to the papers and the links to the slides down below, so you can check it out if you're interested. And with that, I will say thank you for listening.